Hi, welcome to Talking Tech. I'm your host, Marcus Yam, and today we're talking turbo. That's a feature that will increase the frequency of your processor automatically. To tell me more about that today, joining me is Intel Fellow Guy Therien. Guy, thanks for joining Talking Tech.
You're welcome, Marcus. Good to be here.
Thanks. So would you mind telling me a little bit about yourself and what you do at Intel?
Sure. I've been at Intel about 30 years, and I concentrate nowadays in performance segmentation, that is increasing the performance of our products to deliver real end user value.
Great, thanks. So I know we're talking about turbo today, so I want to share kind of my own experience of what turbo means to me, what kind of comes to my mind. So when I was younger, my family had cars from Sweden. And I remember my dad got this new car and he said it's a lot faster and it's because it had a turbo. So that's my first association that turbo means faster. Later on, we got a PC with a 486 CPU in it. And I remember on that PC, there was a button on the front of the case next to an LED that said 33 megahertz. And when I pressed the turbo button, it said 66 megahertz. Now I know that was a very clever trick to kind of get the most performance out of 486 while maintaining compatibility with older programs. But I knew that at that point, turbo had some association with frequency. And I think that still carries through to today. So can you tell me more about the relationship between frequency and performance?
Sure thing. So generally speaking, frequency is associating with what we call the clock speed of the processor. So clocking is an electrical signal that goes up and down, and that's called a clock. We can also call that one cycle. And so how many cycles per second, or how many times the clock goes up and down per second, is what we consider frequency. So within the processor itself, you get a certain amount of work done with every clock cycle. So higher the speed or higher the frequency, the higher the amount of work, and thus the higher performance that you get.
And to distill it down, when you mention these cycles, it's also another word for this is hertz, right? Is that correct?
Yes, so we measure the speed in hertz or megahertz or gigahertz.
Okay, so we're going up to billions gigahertz is billions of hertz per, or cycles per second? Do I have that right?
I believe you do.
Okay, all right, I've been doing my homework. So let's dig a little bit deeper before we get to the term turbo. I know there's been other kind of frequency-related technologies with our Intel processors, including SpeedStep and SpeedShift.
That's right.
Can you tell me about those and how those relate to frequency and performance?
Sure. Prior to the introduction of SpeedStep technology, we had one frequency and one voltage to reach that frequency. But because power is related to the square of the voltage and related to the frequency, as you increase frequency, you have to have a higher and higher voltage, and that voltage is squared to the power. So the introduction of SpeedStep said, well, if we're running, sometimes we only can run at a lower frequency, we only need to run at a lower frequency, a lower speed, because the demand is low. And other times we will run at a higher frequency when the demand is high. So we're going to switch between voltages and frequencies in pairs. Some when we're low and some when we're high, and that will be a better, more power efficient approach. And so this was the adoption of the SpeedStep technology, and we provided that capability within our hardware. And also we provided an interface that allowed the operating system to find out how many of these voltage frequency pairs that we had, or we call these P states, and allow the operating system to select which one they wanted, depending on the demand that was placed on the system.
So if I understand this correctly, SpeedShift and SpeedStep were created for power and efficiency considerations.
So SpeedStep, which was the first implementation of voltage frequency pair switching, was indeed for getting the most performance within the best power. SpeedShift is a different technology that we can talk about next.
Okay, so tell me about SpeedShift.
Okay, so SpeedShift, as I mentioned previously, SpeedStep was when the OS controlled which P state they're in. SpeedShift is a mechanism whereas the processor itself looks at the demand placed on it and adjusts the voltage and frequency according to its own decision making inside its own algorithm.
So SpeedShift is just, not to simplify, but it's a more advanced iteration of SpeedStep.
It is in many ways. It's more autonomous. It's hardware autonomous. It actually allows you to switch voltage and frequency at a much higher rate than was be able to be done previously with an OS-based control.
Okay, so does this bring us to turbo yet? Is turbo the inverse of SpeedStep, where SpeedStep would be looking at frequency and powering down. Is that one way to think of what turbo is, or is that?
I wouldn't put it exactly in those terms. So let me say it in the way I would consider it. So SpeedStep was selecting voltage frequency pairs that were available from the processor. When we manufacture parts, we assure that the parts run at the specified maximum and minimum voltage and frequency. And that's also when running certain specified workloads within certain power. So this is assured by manufacturing to be able to operate within those spec conditions. Then there is the concept of turbo where it's opportunistic. Outside of those conditions, we may have opportunity depending on the workload that's running, the temperature of the ambient environment, and you could potentially get to much higher performance, but I can't necessarily assure that every part gets the identical performance within that power outside of what we call the manufacturing assured range. So turbo is the range above the range that we have assured in manufacturing, and it can deliver a significant number of bins of performance. That's hundreds of megahertz times 5, 6, 7, depends on the product. Can even be more.
So when people see on their processor specs, they see a base frequency and then a turbo frequency or max turbo, that's what you're referring to.
Yes, but it depends on the kind of turbo. So we have single core turbo, and then we have multi-core turbo. Most likely, every part that has a single core turbo, all parts can reach that. It's when you get to the multi-core turbo, when you're running a very heavy workload, not all parts can necessarily get that frequency for all workloads that you run. Okay,
and I know that Intel has several different types of turbo technologies. So could you give us an overview of, from the evolution of turbo?
Sure thing. All right. So as I mentioned, we have an assured range, and then outside of that assured range, we have a turbo range. Okay. Historically, within the turbo range, every core in the processor could get to the single core max. But it turns out through natural manufacturing variation, some cores are actually better than other cores, and they actually have higher performance capability at the same voltage as others. So this was an alien concept to operating systems to provide diversity amongst them. So we pioneered this technique. It's called Intel Turbo Boost Max 3.0, where some cores might be favored or considered to be higher performance than other cores. And this was implemented first with our silicon and our own control software, and then Microsoft adopted the control of this. So Microsoft's Windows operating systems and then Linux operating systems understand that some cores might be higher performance than others, and they utilize them as possible when there are workloads that are demanding. We place those workloads on those higher performance processors first. So this is Turbo Boost Max 3.0 as opposed to the standard Turbo Boost 2.0.
So just to simplify things, what is the key difference between Turbo Boost 2.0 and Turbo Boost Max 3.0?
The main difference is that in Turbo Boost 2.0, the maximum frequency of all the cores is the same. But in Turbo Boost Max 3.0, some cores can be higher frequency than others. And sometimes they can be levels of performance above the others.
Okay. And there are, since Turbo Boost Max, there are other types of adaptive turbos or thermal related turbos. Yes. Can you tell me about those too?
Sure. So we have a feature known as thermal velocity boost. And thermal velocity boost takes advantage of certain aspects of temperature to determine that potentially a lower voltage could be used to get to the same frequency that would not be possible otherwise. As you can imagine, we're extremely quality focused at Intel. And that means when we manufacture, we make sure that the part works within our specifications, and we also need to make sure that the part does not wear out before we expect it to wear out. So there's always a concern to make sure that our test programs that test processors perform the right tests in order to ensure the quality that we need and that end users need to have. And so we have to be very careful. But there are some parts in some cases and sometimes that we can detect when it's what we might call safe or not cause an adverse impact to wear out to run at higher frequencies using the same voltage. So this is the kind of technology that thermal velocity boost is. It looks at the temperature and says if the temperature is below a certain threshold for a certain part, we could actually run at a higher frequency.
So on the user side, if an enthusiast is building a PC and has a very robust cooling solution, that would mean the thermal velocity boost would actually be able to activate or kick on to a greater degree.
That's right. And so if you're an end user or even an OEM who is investing in the power delivery and investing in the thermal solution that's provided in the system, we believe that if you invest in those things, we should provide means to allow you to realize more benefit from having made that investment. So thermal velocity boost is a way to provide that.
And as a person who builds his PCs, I definitely think of that as I can choose my cooling solution, but we should be clear that this also extends to notebooks and other form factors where it's really up to the system designer and the OEM.
Yes, and of course, as you can imagine, the form factor plays into this. So there are trade-offs to be made across all form factors with regards to the cost of the cooling solution that are implemented, the size of the platform, and they all play together to give you different kinds of performance based upon the processor features that are supplied.
I think you gave me a clue a little bit earlier just to go back about the difference between Turbo Boost 2 and Turbo Boost Max 3.0 is our shift in architecture going from single core to multi-core to now actually hybrid multi-cores. Does the core count, core configuration influence Turbo, or is that a consideration when creating these technologies?
Sure. As you can imagine, the more cores that you add, the higher the power would be, okay? If you keep the power constant, then you have to reduce performance in order to remain within the same power envelope. So as you add cores, performance will go down in order to remain within that envelope.
And I guess what a simple way for me to think about this is load balancing, where you have a certain power budget and you decide that you've got this multi-core system and you're running a bursty workload and you only need one, maybe two cores. Is the system able to intelligently divert that power to those most favored cores and to just get the maximum performance?
So when you have a large number of cores, large number of logical processors, when work is placed on the system with Turbo Boost Max 3.0, the OS is very much aware of which cores are the highest performance cores, and it places the work on those first. Demanding work, not just low demand work, but high demand work. And then it expands that out to other cores in a succession. So the most favorite cores, the second most favorite cores, maybe the rest of the cores successively. And that keeps the work from causing power to be run unnecessarily elsewhere. So that maximizes performance.
Now you mentioned, thermals are a factor. Again, that's thermal velocity boost. What about when some people think of kind of a floating turbo? Is there an Intel technology for that?
So we do have a technology. It's called adaptive boost technology. This is a technology that came out in the 11th gen processor, and we're also going to supply that in our 12th gen, one of the SKUs in our 12th gen processor generation. Intel historically has had a limit on the maximum speed when a certain number of cores were active. And this was done for various reasons. The adaptive boost technology removes that limit, and it says, let's not have a proactive limit on the frequency. Let's have a reactive limit instead. And so the reactive limit is something that engages the power analysis and or the current detection to make sure that the maximum speed can be attained when there's light workloads, but maybe when there's a heavier complexity workload, the workload may be, the frequency may be controlled or moved down to stay within the power budget. So this ability to naturally float up to the frequency that is possible, that fits within the current and power capability of the processor, is what we call adaptive boost technology.
So there's a lot of these kind of adaptive, almost automatic, you even use the word autonomous technologies in the suite of turbos. Is there anything that the user needs to do to, take advantage or make best use of them, or even to activate these technologies?
Generally speaking, no. So the concept is that these should just be seamless and they should just work. These are generational improvements to try to get every little last bit of performance out of your processor. In order to help that, the environment and the cooling and the power delivery needs to be there to support it. So again, as the OEM and or the end user invests in these capabilities in the system, we want the parts to have capabilities that naturally are exposed and the end user get benefit in that in terms of performance when they're employed. And
these technologies, what is the, aside from, getting more work done in a given period of time for processors, who is this technology designed for? Who's the ideal user who would benefit the most from these turbo technologies?
Okay, that's a good question. So generally speaking, there's a couple kinds of performance that you might say you get benefit from. One is in terms of responsiveness. There is a natural flow to working, right? When you're working between tasks, switching between tasks, you want to make sure that there's no lag. Whenever you mentally think, oh, I had to wait for that, it's irritating, it breaks your flow, right? Okay? So the first aspect of turbo is making sure that we can race up to an appropriate clock speed to give a responsiveness as quick as possible. The other aspect of turbo is what I talked about is non-guaranteed performance within power. It still gives you great performance, but I just can't guarantee it on every part to be the same. And that continuous turbo capability is something you might see when in content creation, when you're doing an encode or a transcode or things like that. So turbo just gives you higher performance within the power envelope, and it also gives you peak performance for responsiveness.
And when you talk about responsiveness, how quickly, I know these things happen, they switch billions of times a second, but how quickly are these cycles, clock speeds, able to ramp up in response to?
We can change every millisecond.
Okay. So really, when you talk about lag, there isn't going to be any lag.
Well, none that's associated with the processor clock speed changing. Right. Of course, you also have software overhead, and you perceive the lag in terms of what's displayed on your screen via the application and the operating system. But this is much better than it was historically, and so there is a tangible end user experience delta. And if you heard the Intel Evo branding, right, that is also a way to ensure that the system that has that brand is meeting certain responsiveness requirements to deliver that great experience.
So with all these technologies, which you've been working on for so long, what was one of the most challenging technology aspects of turbo to bring to market and make work reliably?
Myself and my colleague, Barnes Cooper, also an Intel Fellow, went up to Microsoft, and we told them one time in a meeting, says, you know what? We are going to change the voltage and frequency of the processor on the fly. And so that was a big step, right? To be able to have a modern operating system that changes the voltage and frequency on the fly was the big step forward. The turbo aspect of it is just associated with whether or not we assure the entire range. There are great things associated with the tricks we went in originally to make turbo possible. Like I mentioned to you, SpeedStep technology was not designed with turbo in mind. And so we did a small 1 megahertz bump in the control that meant that the hardware could take over and manipulate, 6-7 bins of performance above that. So that was pretty fun to be able to take interfaces that were meant for one thing, add turbo, and then see them used for a different purpose, and very successfully. And then, of course, when we went to SpeedShift, then we finally comprehended the entire range, and we said, look, we have a assured range, not so assured range, and we talked to the ACPI spec folks and Microsoft engineers, and so it was great to see everyone lean in to start to implement OS controls for turbo, rightfully understood and comprehended.
So lots of work by you, colleagues, even partners. Do you feel that sure, enthusiasts, gamers, people who care about performance really understand and appreciate turbo, but overall, do you feel that this technology has been appreciated and given enough of exposure?
Yeah, my personal view is that end users have a very difficult time in selecting their systems and what to buy. You usually ask your neighbor, what should I get, right? But the word turbo has become synonymous with performance. And it is something that people will look for when they buy a system. Then we actually deliver that performance in those systems. So from a perspective of actually understanding exactly what it buys you and what they perceive it, I don't think that people really get it. But they do know when that feature's on there, you definitely get higher performance, and it has become a buyer's choice. And it does deliver that performance. It's just, do people really understand exactly how much it gives them? I don't think so, but the proof is in the pudding. As we say, look at the benchmark scores, you see a significant delta between having turbo and not having turbo, because there's so much opportunistic range that we provide in turbo.
So with all that, all your technical background, all your technical expertise, and telling that, hey, to help people understand the value of turbo more, I'm going to borrow a page from Reddit where they have this subreddit called Explain Like I'm 5. Can you try to explain what turbo is to a 5-year-old? How would you do that?
Let's see. Well, I happen to have a 5-year-old.
Okay. Well, is he like a little mini Intel Fellow too? Because that's a little
bit more ornery, but yes. So what I would probably would not be able to explain it to a 5-year-old. I would just be able to say, they won't understand it. They'll say computers run at different speeds. Some are fast and some are slow. And I'd probably say the turbo is really, really fast, and that's the most they can understand, I think.
That's actually how my dad explained to me about his car with forced induction with the turbocharger. So on that note, I can't think of a better way to wrap things up. We're kind of out of time here, but this has been a very exciting and insightful conversation on turbo. So thanks for joining me, and I hope we can do this again.
You're welcome, and I'd love to.
Thanks, Guy.